Hello everybody, welcome to Blue Marble Science. Today I'm asking the question, has Nathan Oakley finally figured out perspective? Well, what do you think? You know, after all this time, it's hard to believe we still have to talk about this. Personally, I think Nathan will figure out perspective about the time this happens. So tell you what, let's light this dumpster fire and have a little fun. On this particular day, Nathan's victim is a guy who calls himself Wiggles. Whatever. And Wiggles is trying to explain to Nathan how the radius of the Earth can be estimated just using a photograph. But of course, Nathan can't stop being Nathan long enough to learn anything. Now, the photograph in question is this one. It's one taken of Toronto. And while I might not be the sharpest tool in the shed, I'm pretty sure what Ray Charles could see that the entire sky dome is missing in the photograph on the left. Now, realizing that this sort of photograph is pure kryptonite to the flat Earth movement, Nathan is going to do what Nathan always does, and that is deflect the conversation in a different direction completely. He'll bring in the Rayleigh Criterion, he'll talk about perspective, anything he can think of to get away from the fact that you can't see the damn sky dome. So let's have a listen.
Does your calculation include the actual optics that will be used to compare when you compare your model to reality?
Well, the way that we do, it's just like really dead simple almost. It's like this is like, I probably shared this image before. It's just like the ocean getting in the way of distant objects.
Yeah, sorry, my question again, just so it's repeated. In your calculation for what you have already declared is simply geometry, have you accounted for optics?
So what do you mean by accounting for optics?
Could I interest you in some red herrings, sir?
What are optics, Wiggles? Are we using optics for these pictures?
Well, they're pictures like we
so
take
that would be a yes then, would it?
Right,
just a simple yes or no. Are we using optics for these pictures? Yes or no?
That's sort of a weird question. Like
it's a yes or no question. Yes or no? Were these optical representations of reality using optics to attain them? Yes or no? I'd have thought the answer was obvious. Clearly, Wiggles thinks it's a trick question.
Well, I mean, the pictures were taken by a camera.
So would that be a yes, Nathan? These absolutely utilise optics.
I guess so, sure.
Yes, excellent. Now show me where that's accounted for in your calculator, please.
Well, the calculator is just...
Put your calculator on. Put it on screen now.
Okay.
Where is the optics accounted for? Namely, the Rayleigh Criterion. Where is it?
Okay, that's enough of that foolishness. I would have thought after the spanking Nathan took from Dr. Bob a week or so ago, he would have left the Rayleigh Criterion alone. But he didn't. The Rayleigh Criterion is simply the accepted criterion for determining how far apart 2 points of light can be, and you still be able to resolve them as two separate points of light. At some point, they get so close together that they become unresolved, simply 1 point. There's a formula for that, and for the example that Wiggles was using, he says his object is 39 miles away. I assumed he had a camera with an aperture of, say, 25 millimeters. I used a wavelength of light of 500 nanometers, and if you calculate the Aries disk radius from that, you get about 5 feet. 5 feet over 39 miles.
No, what the curve calculation, all it does is just calculate the height of the height of the obstruction of the object.
So let me get it straight. You're going to compare something that's only dealing with geometry with something that's optical in nature, Well, no, Wiggles, that's totally incorrect. That would mean that you would ignore the very aspect of optics that's been used to acquire the thing you're going to compare to a geometric-only calculation.
How about a nice word salad to go along with your herring?
Well, so Nathan, what all I'm doing, right, is like the y. I'm just letting y be the height of the obstruction of the object, right?
Sorry, you've just shown us that you'll compare it to optical-based information. And I've asked you to show me, you're yet to do it, where optics are taken into account. And you've said it's geometry only. Therefore, not comparable to the pictures you've shown. I don't know why you've shown them.
More word salad, sir. You know it's all you can eat on Wednesday.
What's on screen now, this picture that I've got on screen, includes perspective. It also includes diffraction limit based on the aperture of the camera. Now, those things which are absolutely present in this picture, i.e. things that are in the near foreground, like this tree, for example, can seem like they take up half the frame. Yeah? Now, I'm not going to give you a feet and inches measurement. I'm going to say by virtue of perspective, this tree literally takes up half of the frame. Whereas over here on this mountain, this tree takes up 16 pixels. So it's the same size tree in feet and inches, but your calculation doesn't take that into effect. In other words, the things that are in the near foreground will have the same measurement attributed to them as the things in the far distance. Therefore, optics, the thing you are comparing it to, is not included, therefore not comparable, Wiggles.
Well, Nathan, with all due respect, what you're getting on with is bullshit.
So you're saying that you can just exclude the very nature of the thing that took those pictures and the workings of those things, optics, when comparing it to an optics exclusive calculation, and you think that's reasonable?
The problem, Nathan, is you don't understand a curve calculator. You don't understand what it is or how it works. This is straight out of the Metabolic curve calculator. Go to their website, open it up, scroll down to the bottom, and you will see this diagram. There is no place in this sort of curve calculator for perspective because it isn't used, it isn't needed, it isn't required. What you need to know, look on the left, see the little circle? You need the height of the viewer. The height of the viewer, based on the radius of the Earth, is going to determine the point of the horizon. Once you know that, you can draw a tangent line from the observer's eye through the horizon point and all the way out to the object you're observing. What it is designed to calculate is the amount of hidden distance at the object being observed. Those have to be the actual sizes of the objects. Perspective cannot be taken into account here. That would make absolutely no sense. There is another kind of curve calculator. There is one that does take perspective into account because it simulates what you actually see. The Metabolic type calculator uses simple geometry. It is only designed to predict how much of an object will be hidden by the horizon. That's all it does. Perspective doesn't come into play with that kind of calculator. It couldn't. Now, for people that don't understand that sort of geometric presentation, which you obviously don't, Walter Bislin has this calculator, which gives you a visual representation, including perspective. I've got two objects here. Target 1 is on the left. It is 75 meters tall. 75 meters tall and 5,000 meters away. Target 2 on the right is 150 meters tall, but it is 10,000 meters away. Twice as far away, but twice as high. Just like perspective says will happen, they appear to be the same size. If I make the far object the same height as the near object, there you go. The far object is twice as far away and it appears to be half the height. This kind of calculator takes perspective into account. So Why don't we knock off the nonsense and stop talking about this? Let's go back to the picture. The CN Tower is 1,815 feet tall. The Sky Dome is 312 feet, according to the information I can obtain on it at its highest point. But that building is actually about 20 feet above the lake level here, so that makes it around 330 feet. And then probably include another 20 feet for the upper structure, just to be on the safe side. We'll say the Sky Dome is roughly 350 feet to the top. Now let's do this. Here is a representation of those two structures. A 350-foot structure on the left and an 1,815-foot structure on the right. The distance to them is 205,920 feet. That's 39 miles. This is the view in Walther Bisland's calculator that you would expect if the Earth were flat. Let's change that. Let's see, I have to go back to, that's the flat Earth setting. Let's go to the globe. Uh-oh. The tower's still visible, but the stadium disappeared. And the stadium disappeared because 613 feet are missing. 613 feet of the CN tower is obscured by the horizon. This is very clear proof that what you're seeing is the curvature of the Earth. And then we come to this train wreck. Let's watch as one of Nathan's lapdogs accidentally proves how the horizon obscures objects.
Hey, Wiggles, before you leave, or before Nathan ends, I just want to counter one of your points. Can you bring up your picture of the CN Tower again, please?
I can do that. Here it is.
So part of Nathan's point is if you're not taking in optics and atmospherics into account, into your equations and into the maths and your tests, then you're not taking into account the real world reality and real world scenarios. So everybody can see on the left, there's sort of a blank test, and then what you actually see, right? And it says, why is the bottom missing? So if I can present real fast.
Well, I mean, the bottom is missing because the ocean is in the way, but go ahead.
Okay, so that's the whole that's the whole point of this hour-long conversation with you, is that is it's an assumption to say that the bottom is missing because of X when you haven't proven X. Okay, so let me take over and show you a demonstration that we can do and show in real world, based on real world phenomena, based on atmospherics and how we know the atmosphere to work. So I'll share real quick, and then Nathan probably will round out the show, but if he hasn't already. Okay, can you see my screen?
Yeah.
Okay, you see the CN Tower here?
Oh, I saw this before. It was a pretty cool trick.
Yeah, it's really cool because it makes perfect logical sense. So why can I not see the bottom of the rest of the city in the CN Tower? Is it because it's over a curve?
Yeah, so my rebuttal to this actually was, what happens if you lift the camera up higher? Do you then see the bottom of the tower?
That's not the question. Why can't I see? You said you can't see the bottom of the CN Tower because of the water is in the way because of a curve. Why can't I see it in this example? Is this table curved?
No, well, you're refracting the light around.
Oh, you're refracting the light. Now, what would cause refraction in the real world? The atmosphere? So let me hit play and watch as he moves closer to this this lens, which is acting as an atmosphere. Now look at that. As he gets closer, wow, what do you know? You can see more of this tower and the bottom of the buildings. And when he does his blink test, it matches up pretty much perfectly with the one you did.
That short video clip was actually taken from a Rob Skiba demonstration. What Rob did was take a photograph of Toronto, put it in a box behind a Fresnel lens. Now, Fresnel lenses are used in lighthouses and lots of different video applications and light applications, not the least of which is the landing system on aircraft carriers. Depending on the position of the observer, they can make objects behind them appear to be in lots of different positions or just totally disappear. So it's really a very disingenuous sort of a demonstration. It has the same effect as if you had dropped the object below the top of the table. And obviously, what would happen if you did that is you simulate the effect of the curvature of the Earth. So congratulations, Einstein. You proved the Earth is a sphere. You know, I think that's about all we need to say. I believe this nonsense is busted. Hey, please don't forget to hit the like and subscribe buttons, and we'll see you guys on the next one.